Hello everyone, Mark Dijkstra here, your friendly neighborhood finance professor, and I'm here to talk about lecture 2 for Finance 2, and now we're going to talk more about portfolios and capital asset pricing model. Again, I have the Mentimeter link right there, so if you click on that, you can already go to the Mentimeter exercise that I'll get to later in this lecture. So last week we already talked a little bit about how to measure volatility. So we measured volatility with the variance and the standard deviation. We got an idea of how to estimate returns and volatility from previous historical data. And then I already gave a little bit of an idea of, hey, how does diversification lead to less risk? Today we're going to expand on that. So we're going to start with calculating covariance correlation. So I'll also give you a little bit of an intuition of why we want to know about covariance correlation. And after that, we'll go into the role of covariance correlation into diversification, get to the efficient portfolio, and finally get to the capital asset pricing model. So maybe some of this is a repeat of what you've already done in Finance 1. So if you already know all this stuff, well, that's great for you. You can simply sit back, relax, have a nice cup of coffee while you listen to me talk. But hope this is some pretty important stuff, because the capital asset pricing model is really one of the main models that's used to determine rates of return in finance, and beta is one of the main measures of risk. So I really want to make sure that everything about the capital asset pricing model is well proved, is well understood. So that's why I'm taking some time here to maybe repeat what you already know, but hopefully leads to better understanding even if you already know. So last time we talked about, hey, how does diversification work with portfolios? So if we looked at these returns for North Air, West Air, Tex Oil, we could also see that, hey, if we combine, let's say, North Air and West Air into a portfolio, the expected return was the same as the underlying stocks, or somewhere in the middle of the underlying stocks. In this case, they have the same expected return. So that the return of the portfolio is also the same. And then, but we saw that the volatility was lower. And then if we combine Tex Oil with West Air, the volatility is even lower. So why is the volatility so low for this portfolio with Tex Oil? Well, that's because these two stocks have negative correlation. When one goes up, the other goes down, more or less. And if you have that, then combining two shares will typically lead to more diversification, even if positive correlation between two shares, so if one goes up, the other also goes up, also leads to diversification, but less so. So here you see more or less that, well, there's this crucial role for correlation, covariance in the determination of portfolio returns. So if this is such an important factor, so covariance correlation, then of course we need to start calculating it. So what are covariance? What are covariance and correlation, and how do we measure that? So covariance tells you something about if one share moves from its expected value, what happens to the other share. More formally, it is the product, the expected product of the deviations of two returns from their expected value. So here, rather than taking the variance, which is the squared value of the deviation from the mean, here we take the expected value of stock I times the deviation of stock I times the deviation of stock J. And if we take that from historical data, then of course we subtract the mean, right? So we take what is the actual value of the return of I minus the average value of the return of I, and multiply that by the return of J minus the expected return of J. And then divide by t minus 1. So again, because we're taking actual data to estimate the mean, that means that we're taking away 1 degree of freedom. And that means that we can divide by 1 minus t minus 1, 1 over t minus 1, rather than divide by t. If you then have positive covariance, that means that they're moving together. So if one value, the value of the return of one stock, is above its expected value, and you then have positive covariance, you would also expect the other to have positive value compared to its expected value. And if they move against one another, so if you expect one to be very positive, you expect the other to be very negative, well, then you expect if one has positive deviation, the other to have a negative deviation. So covariance tells you something about how do the returns of two shares co-move. So do they move together, positive covariance, or do they move against one another, negative covariance. One thing to note though is that the actual number that you get, and especially the size of the number, is pretty hard to determine. It's pretty hard to interpret, and we'll get to how we can deal with that. As always, I have some questions here to kind of make this a bit more concrete and to also get you guys to work so that you don't only have to listen to me and you can also do something for yourself. So let's go to Mentimeter. And let's look at the first question. So again, these are the more or less the simplest types of examples that I can find, because I want to talk a little bit about what is the idea behind these calculations, more than I want to challenge you with these questions. So try at home, try to follow along. Of course, you can do what you want. You can also wait for me to explain immediately, but I promise you, you will get more from this if you try along at home. So up to you, more or less. So here we have two returns. So for stock A and B at T1, 2, and 3. And stock A had 10% in time 1, 5% at time 2, 3% at time 3, and stock B had 6% at time 1, 7% at time 2, 2% at time 3. And now my question to you is, what are the average returns? I'll give you a moment to pause me. And yeah, this should be 6% and 5%. So how do we do that? Well, here I have my returns in Excel, because that is very easy to calculate the returns then. So if I want the average returns, well, I can simply add up values for A and divide it by 3. What I can also do is use the command for Excel called average, and then that should also give me the average. So also 5%. So it doesn't really matter which of the two I use, whether I use the average function or if I simply add them up, gives me the same value. Can also can then go to Mentimeter question number 2. So same returns. We had the averages of 6% and 5%. Now my question to you is, what is the covariance between these returns for A and B? I'll give you a moment to pause me. And then the correct answer is 0.00055. So how do we do that? Well, the covariance is the product of the deviations of A and B from the mean. So let's do that for A. So for A, it's going to be 0.1 minus 0.06. So let's log this one in. And let's call this deviations from the mean, from the average for A and for B. Then let's copy and paste this. Let's see if I'm doing all of this correct. I think I am, but yeah, so for B, yeah, I logged the right cells in, so for B also shows me the deviations. Then I can take the sum here. So let's take, well, let's take the sum here. Yeah. Why? No, don't want to do that. Let's do two things. Let's start with calculating the variance for A and for B. Let's start with calculating the variance, because for the variance we need the squared deviations from the mean. So let's add all of these together. Let's square these and add all of these together. And then divide all of this by 2, because we have 3 observations, so t minus 1 is 2. And then I can do the same for B. And then let's also calculate the covariance. So the covariance, what should we have? So that should be deviation of A from the mean times the deviation of B from the mean plus deviation at time is 2 of A from the mean times deviation of B at time 2. plus, well, the deviation of A at time 3 times deviation of B at time 3. And then divide all of that again by 2. So that gives me a covariance of indeed 0.00055. All right, fine, well enough. So, as I said, the magnitude here is not always easy to interpret, and that's where we come up with this measure called correlation. So correlation does tell you a lot more because it's a lot easier to interpret. So correlation is very similar to covariance in that it measures how do two stock returns move together. So do they move together positively? Do they move together negatively? But the correlation will always be a value between -1 and +1. And -1 tells you that the stocks move perfectly against one another, and correlation of +1 tells you that the stocks move perfectly together. So how can you interpret the correlation coefficient? Well, you can interpret by saying, hey, if the return for the stock I changes by some percentage, we would expect the return for J to change by the correlation coefficients times that percentage. So if the correlation coefficient is exactly 1, so they move perfectly together, well, then you would expect if I goes up by 6%, then J would also go up by 6%. If it's perfectly negative, then if I goes up by 6%, you would expect J to go down by 6%. And of course, all these values will be somewhere in the middle. Let's try and calculate the correlation. So given our variance-covariance matrix, what is the correlation between returns A and B? And so here I've presented this variance-covariance matrix. So as we saw before, we calculated the variance for A, the variance for B, and the variance-covariance matrix simply shows you, well, what is the covariance between these chairs. So for this first value here is the covariance between A and A. So that of course is the variance between A and A. This value here shows you the covariance between A and B. And here it shows you the covariance between B and A. Of course, the covariance between A and B is going to be the same as the covariance between B and A. So that's why these numbers are exactly the same. And then down here we have the variance for B. So if we would have a third stock in here, then the variance covariance matrix would show the variance of share C down here. Over here it would show the variance between A and C. Again here it would also show the covariance between A and C. And here it would show the covariance between B and C, and it will also show the covariance between B and C right here. So given this variance covariance matrix, so we know the variance of A, variance of B, covariance between A and B, my question to you is, what is the correlation between the returns of A and B? And I'll give you a moment to pause me. So what is the correlation then? Let's calculate this. Or maybe first show the correct answer. So I have 58% here. So let's see if we can come up with that number as well if we calculate the correlation. So the correlation was the covariance over the standard deviation. So we don't have the standard deviations yet, but we do have the variances. So we can simply take the square root to obtain the standard deviations. And then that should give us, indeed, it's 58%. So one thing that's nice about Excel is that you can also ask Excel to do all the calculations for you. So for instance, rather than calculate all these deviations from the mean, I can simply ask Excel, okay, why don't you calculate the variance for me? And then I have a possibility of using var.p or var.s. var.p is, hey, if you know the population mean, then you can do this if var.s is if you estimate the population mean. So typically always use .s because, well, in reality you don't know what the expected value is going to be. You simply need to calculate the average. So practically what this does is var.p in this case would divide by 3, var.s divides by 2 because, well, because we took away a degree of freedom. So let's see if this gives us the same number for the variance. Indeed it does. And for B, we can look at if we find the same, and indeed it does. So we can do also the same for the covariance. Covariance.s, and there it asks us for 2 arrays. So yeah, let's use these 2 arrays. And indeed also shows us the correct covariance there. And then let's also do correlation between these 2, and that should also give us exactly 58%. So you can use some shortcuts in Excel. So why did I use the roundabout way and not just input this formula for the correlation? Well, if I simply input the formula for the correlation, becomes a bit of a black box, right? It's like, yeah, we drop in some numbers and then ooh, a solution comes out. And of course we don't want that. We want to know exactly what goes in here. But it is reassuring that we get the exact same values that Excel does. So likely both we and Excel are doing the right thing. So correlation, I already said, it's always going to be between -1 plus 1. So if you would find a perfectly negatively correlated data series, you would expect this exact negative relationship, so a negative straight line. For correlation of +1, you would find this exact positive line, and if they're uncorrelated, it's more or less like a cloud, right? And then you find no correlation whatsoever. So then, of course, we want to start calculating a little bit, because if we start calculating a little bit, we can actually calculate, hey, what is the expected volatility of a large portfolio? And then hopefully once we have calculated, hey, what is the expected volatility of a large portfolio, we can also formalize a bit more of how diversification affects this volatility. So let's formalize a little bit. So this is going to be pretty math heavy. Of course, I don't expect you to reproduce this, but I wanted to show you this because for the end result, the capital asset pricing model that we end up with, it is important that you understand it. So you don't need to reproduce it, but you do need to understand what's going on. And so let's calculate what is the variance for portfolio. So I'm going to start at the top left right here. So the variance of portfolio is going to be, well, its expected squared deviations from the expected value, right? So in this case, the expectation of RP minus expected value times RP minus the expected value. So these are simply the squared deviations, right? But then if we have this is like I have the covariance of a portfolio with itself. So this is a bit of a roundabout way of writing this out, but it becomes useful in just a second. So the variance of a portfolio is like the covariance a portfolio has with itself. So why is it convenient to write it in this way? Well, because you can write out one of these terms, so in this case the first RP, as simply its portfolio returns. So portfolio returns, go back to the previous lecture, is simply the weight of each of the underlying shares that's in the portfolio times the return of that share. So if I sum all of those up, then I get the portfolio returns. So let's write that out. And then we get that, hey, the covariance of a portfolio with itself is the covariance of, so the sum of these weights times the underlying shares with the portfolio. Then we use statistical rule that the covariance of a sum is the sum of covariances. So again, this is more of a statistical thing than a finance thing. But if you want me to write this out and to prove this to you, I'll happily do so. Let me know, send me an email beforehand so I can prepare a little bit. Again, it's been 10 years since I did this kind of stuff. So I'm happy to show you I can do it, but I will need a little bit of time to prepare, so send me an email. For now, please note that, hey, a statistical rule is the covariance of a sum is the sum of covariances. So here I can simply take out the summation sign and say, hey, the covariance of the sum of all these of this sum is the sum of all these covariances. And then, so then I have that, hey, the variance of this portfolio is the sum of all the covariances of the weights times the returns with the portfolio returns. And then because the weights are constants, I can pull those out as well, so that I'm left with this summation of the weights times the individual covariances. So the variance of the portfolio is the sum of how the individual shares co-vary with the returns of the portfolio. I can also write this out a little bit further. So if I take this, so that the sum of xi times the covariance of Ri and Rp, I can also write out the second Rp as, again, the sum over all these shares, so xj times Rj, and then take again the fact that, hey, the covariance of a sum is the sum of the covariances, and again, in the same way as I did above here, simply pull out these portfolio weights, and then I'm left with this expression where we say, hey, the variance of a portfolio is simply the portfolio weights times the covariances of the underlying shares. To make this a little bit more concrete, let's write this out for a two-stock portfolio. And so for two-stock portfolio, what should come out is, if I follow this formula and then I have two stocks, x1 and x2, r1, r2, then I would expect here, well, a sum over all the shares 1 and all the shares 2. So what I would expect is, first of all, well, x1 squared, because, well, we also count the variance of, or the covariance of Ri with itself. So x1 squared times the variance of R1 plus x1, x2 times the covariance between 1 and 2 plus x2 times x1 times the covariance of R2 times R1 plus x2 squared times the variance of R2. So let's see if that actually comes out. And so if we have this two-stock portfolio, so let's follow the exact same steps as we had before. So then the return of the portfolio is x1 times r1 plus x2 times r2. So if we then write out the variance of this portfolio, this should be the covariance of this portfolio with itself, which is equal to, well, let's write them both out. So here the covariance of x1 r1 plus x2 r2 with x1 r1 plus x2 r2. So since the covariance of a sum is the sum of covariances, let's take the first part. So here the covariance of x1 r1 with x1 r1 plus x2 r2 plus the second part, so the covariance of x2 r2 with x1 r1 plus x2 r2. And then let's also write out the second part. So here, the first thing here, this is the covariance of x1 r1 with x1 r1 plus x2 r2. So this should be equal to x1 r1 with x1 r1 plus x2 r2 with x1 r1, etc. And then if we write that out, then we have here the covariance of x1 r1, x1 r1. So this should be x1 squared times the variance of r1 plus the 2 times the covariance of x1 of r1 r2 times x1 x2 plus x2 squared times the variance of r2. And let's do a little Mentimeter exercise with this. So suppose we still have the same returns. So we still have 10%, 5%, 3%. We have the following covariance matrix. What is the variance of a portfolio of 50% A and 50% B given the covariance matrix? I'll give you a moment to pause me. And then let's show the answer. So here the answer is C. So let's see if we can also calculate this. And so if we want to take the variance of the portfolio, let's first calculate, hey, what is the return of the portfolio? Well, the return of the portfolio is simply 50% A, 50% B. And then if we calculate the variance of this portfolio, let's do var.s. Then the actual variance is, well, 0.00078. Let's see if we get the same with our calculation. So it should be the portfolio weight of x1 squared. So in this case, 0.5 squared is 0.25 times the variance of A plus 2 times, well, x1, x2, so 0.25. So 2 times 0.5 times 0.5 times the covariance. So the covariance I have over here, plus 0.25 times the variance of B, and that gives us also the exact same value. So that is very reassuring. So this gives us an idea of, hey, how should we calculate the covariance and correlation of this large portfolio? And then in the second part of this lecture, I'm going to show you, hey, how can we use this calculation of the variance of this portfolio to show you how diversification adds exactly or reduces the variance of this portfolio. See you.